Hello and welcome to this new video. Today we are going to talk about the second extended file system, history, schematics, and more coming up. So my goal today is to explain to you how the second extended file system works under the hood. Not how to mount it, not how to format it, but really how it works when it's writing on the drive. But for that, we will need to go back in time, back to 1991, where Linux was at its first year of life. And it had only one file system, that file system being Minix FS. Now it makes sense that we're using Minix FS because Linux was based on the Minix operating system. And Minix FS had one big advantage, is that it was really simple. And in the file system world, well, simple means stable. So Minix FS was a good thing for a good while, but in 1992, there was a push for something different. So they implemented VFS, the virtual file system, to the kernel, which if you watch my video, you already know, but it's the middle layer in between the file system drivers and the rest of the kernel and the user space in order to be able to communicate between the two. So before that, if you wanted to communicate with another file system, you really couldn't, because if you wanted to, you would need to compile a whole new program or have some special code to work with that new file system. Now, with VFS, you only need to make code that works with VFS on both sides, meaning that your file system drivers only talk with VFS, and on the other side, if you have a program, well, your database only talk with VFS, so both of them can communicate whatever the file system you have on the actual drive. So VFS was created in 1992, and a good guy named Rémi Card created the first extended file system. Now, the first extended file system, there's a reason we don't really talk about it that much. It's because it wasn't that great. Well, don't get me wrong, it really helped a lot back in the day because, well, Minix was really limited. With Minix FS, you could only have 64 megabyte of file system size and of file size, and you could only have maximum file name of 16 characters, which of course is extremely limited. Now, the first extended file system, your limit for the FS size and the file size grew up to 2 gigabyte, and you could have up to 255 characters of file name. So you already see big improvement there. But the issue came at the implementation, where things weren't really that stable. It could easily become really fragmented. In other words, it wasn't the greatest. Now, that prompted people to start thinking about what can we do better? How do we fix this situation? Because right now we have Minix FS, which is stable. We have EXT, which isn't, but it's great because it's all bigger, but it's not as stable as Minix, right? So we need to fix this. Now, the solution to fix that problem, there were two solutions back in the day. The first one was Xia FS. Now, Xia FS, what they did is that they decided to take Minix and just grow it up. So you take the max file system size, you put it to 2 gig, you keep the same limitation on the file size. Anyway, nobody's going to use more than 64 megabyte of file size. Come on, guys, that would be unrealistic. And the maximum file name is stuck at 248 characters. So that was already better, but not as good as EXT on a lot of things. And there was the second answer, which was the second extended file system. Now, EXT2 wasn't as great as Xia FS as soon as it got out. It took a little bit of time, a couple of months, but it still was better on the long run than Xia FS. The big thing that made EXT2 what it is today is the fact that it's extendable. It's something that you can add on to. Because with the EXT family of file system, it's all built onto one another. In reality, EXT2 is the base on which we built EXT3 and then after EXT4. But even at the start, EXT2 was really just a skeleton for what we could call EXT2++ that was made afterward to make EXT2 what it is today and what we know as this God file system that always existed for us. And just to compare, the max file system size for EXT2 was 4 terabyte and the max file size 2 gigs, the max file name was 255 characters. So we can already see the superiority on that end of EXT2. But like I said, it took a little bit of a short while for it to be as performant and as stable as XeaFS, because XeaFS, well, was pretty much Minix v2. Now let's get on to how EXT2 is actually built and how it actually works. In order to understand how EXT2 works, we are going to need a few little information beforehand. Now, I'm not going to explain everything about the 3 concepts that I want to explain to you, but we're going to give you at least the skeleton so that when we're talking about things, it's not going to be just blank, but we're going to put more inside it a little bit later. So for now, you need to understand what a inode is. An inode is the short for index node. It's a concept that is there to make sure that you have the information about what's in a file. And when I'm talking about the information, you will have the information about where the file is, you will have the information about when the file was created, the permission of that file, but you won't really get that much more. You don't get the name of the file, you pretty much only get what I told you right now. So the inode is just a specific concept, a specific thing that's stored on a drive that's there to give you the time, the place, and the permission of a given file. Now you also need to know what a directory is. Now in this video I will talk about the concept of a directory as a directory table. Why do I do that? It's because technically with EXT2 there's directory with a Y at the end, which is what I will talk about when I talk directory table, and there's the concept, the Unix concept of a directory, and there's also directories, which are the entries inside of a directory table, which you understand, I'm French Canadian, that's going to be way too complicated for me. So directory table mean in traditional EXT2 language directory, but that part of code, that's the information for what is inside a directory. So when we talk about the directory table, it's pretty much a big table that tells you, hey, that's what's before me, that's what this directory is, and that's what's under me. So that's what inside of the directory. So all that information will be inside one table that we will look more deeply after, but just know that there's a table that does this, that gives you all the information of what's inside one directory. And the last one is the block. Now the block is the standard unit onto an hard drive for data. So your hard drive will be split into blocks to make the hard drive more easy to use, to manage. So blocks will change depending on what the user wants, and that's something that actually EXT2 did that other file systems weren't really doing, is splitting things into block, and the block normally are supposed to be the same size as your memory pages, meaning that if you have, for example, an x86 CPU, you would use a 4 kilobyte block size, because pages are 4 kilobyte, you want a 4 kilobyte block size to be able to just throw whatever's in your hard drive onto memory without any loss, without any performance issue, because you're trying to fill something that isn't the same size. And that was changeable depending on what was your page size. That was a big advantage because normally you would be kind of stuck where the creator of the file system wanted it to be. So if it was 1 kilobyte, well, good luck, you've got a 1 kilobyte block size and you're stuck with it, and well, you're losing performance. That's a you problem. You just had to use something that uses 1 kilobyte pages, like whatever architecture used to do that. So now we know inodes, we know directory table, and we know the blocks. So let's get into the actual file system, what you see on the screen right now. So what we have is a sample for a 20 megabyte partition layout using 1 kilobyte blocks. Now we're using 1 kilobyte blocks just to make things as simple as possible for our brains, and also because the resource that I used to make this video used 1 kilobyte blocks. Yes, I'm a little bit lazy like that. So let's start at the beginning, where we see that for the first 124 bytes, we see the boot record. Now it makes sense because the boot record needs to be at the start of the drive. That's just standard procedure. So there's nothing else to say there. But right after, we have the first block group 0. Now, what's fun with EXT2 is that everything is split onto block groups. So block groups are there to make it as manageable as possible and to scale things up. Because if you wouldn't have those block groups, it would be really hard to be able to kind of think about your hard drive when you're going onto the 2 gigabyte or, well, you could have up to 4 terabyte of partition size. So to be able to scale that up that much, you needed to split things down into block groups. And inside each block groups, you would always have the same thing. Now, in this video, we're only covering the revision 0, so the first ever revision of EXT2. Now, I'm saying that everything is under revision 0, but that's not true. There's one exception to this, and that's what you're seeing right now. Because you can see that there's the super block and there's the block group descriptor table, and they get repeated onto block group 1, and they should be repeated onto block group 2, but I was trying to show you the difference between different revisions. So revision 0 has it repeated at every block group, and under revision 1 that's already gone. So they already make it only for certain block group, and I believe the 2 first are always there. So you see there's always change on different revision, but they always kind of keep the same standard way to operate. So now let's just go and zoom in some things to be able to understand it better, right? Let's zoom into the super block. So what we see inside the super block is, well, a bunch of information. What is this information used for? So the goal of the super block is there to give you all the information that you need for when you're mounting the drive. So it's not there to actually help you read data, it's more there to say to you, hey, should we actually run a check right now? What operating system was this used with? Is there any error right now that's going on? And how much data is there on that drive? How much inode is there on that drive? So we need to know that, right? So all of that information will be inside of the super block. And that's why in the first revision, it was repeated on every block group. It's because it's so important. It contains all you need to be able to read your data. Without it, well, it's possible to be able to recreate it, but it's really hard. So really important, the super block gives you everything to be able to mount your file system. Now at the end, you see in green, there's the reserve for upgrade. Now remember, we're talking about the revision 0 here, meaning that we don't have all of the new fancy options of the later EXT2 revisions, but there's a lot of things that they added there, and that's what's fancy, that's what's good about EXT2, is they have a bunch of places where they just leave data to be determined. Let's just, in the future, we're going to probably add some things we don't know right now, but let's put a big place there where we could actually fit stuff to make it work better, faster, or add compression. They just let some place to be able to make it future-proof. So we're going to see that everywhere, but that's the first place where we actually see it. Now let's go back to our partition layout. So that's it for the super block. We now know how to mount the file system. Now, how do we actually read the data on the drive? How do we know where's what? So for that, we will use the block group descriptor table. So the block group descriptor table is, of course, a table. So what we're looking at right now is one entry in that table. So we see for each block group, we will have one entry. So in our case, we would have 3 entries. So one for block group 0, block group 1, and block group 2. Now, what it gives is the information of where things are. So we have where is the block bitmap, where is the inode bitmap, where is the inode table, and after that it gives us some information about is there any free space there? Can we actually write something there? And how much directory are used? And after that we have another place for reserved. So we have place for future upgrades again. So now we have information about how full each of our block groups are, where actually to read the information inside of our block groups. So now we're good to go, right? We can go into the file system and actually read the data. Now let's switch back to our partition layout where we see that we have the block bitmap and the inode bitmap. Now those two are fairly simple. The block bitmap is there to tell you where places is taken on the drive. So if you have a 1, the places is filled. If you have a 0, there's free space for you to write. And the inode bitmap is kind of the same thing, but it tells you where the inodes are to be able to find them more easily. So let's go back to our partition layout, and now let's get to the exciting part, which is the inode table. Now the inode table is a big table that contains all of our inode. So the first 11 entries of that table are reserved. Now most of them were reserved for future-proofing things, but the first and the second one were really important. The first one was there to actually give us the information of where would a broken sector be. Because remember, now we have SSD, we don't really have any broken sectors, and even our hard drive, our HDD, don't really get those broken sectors. But back in the days, it was really common to have an hard drive with, well, a couple of broken sectors. Even some out of the factory would have broken sectors. So you could actually say, hey, that block, and that block, it's on a broken sector. Don't write it because you're going to get not working data. So that was the first entry. And the second one was actually pointing to the root directory. So this is how we knew where to look at to be able to get our root, our slash of that drive. But for now, let's just look at what an inode is, because I've kind of described it really simply earlier, but right now we can go deep into it. So we see that we have first is imode. Now, imode is just telling you what's at the end of this inode. It can either be a file, it can be a drive, it can be, well, a block device, or it could be a character device. We're not getting into that. It could be a directory. So it just tells us what the hell is at the end of that inode. After that, you have the user ID, you have the size of the data at the end of the inode, you have the access time, creation time, modification time, deletion time, group ID, the number of count that has been linked. So meaning that sometime you can have one inode that's linked by multiple directory. You could have 2 files that point at the same place, at the same physical place on the drive. After that, you have blocks, which is an internal function. You don't have to know about it. After that, you have flags, which are there to tell if you can write something or, well, if there's a flag on it. You have OSD1, which is operating system specific command that you can actually put on a file or on a directory to be able to give more information. And after that, you have the iBlock. Now, I'm not going to talk about whatever's in yellow at the bottom because I don't believe that they were in revision 0. But I have no proof of that because it's really hard to know what was when we're talking about EXT2 because documentation is kind of scarce. So I don't believe those were in the early revision, but let's just talk about the iBlock because that's actually the interesting part. Now, like I talked a little bit earlier, the inode contains also a pointer towards the data. So just something that's there to tell you where the data is. So let's zoom inside of the iBlock. And what do we find? We find 12 direct block pointers, 1 indirect block pointers, 1 doubly indirect block pointers, and 1 triply indirect block pointers. What does that mean? Now, first, a direct block pointers, pretty obvious. It directly points to a block full of data. So first, if you need 1 kilobyte file, you can just use one of those pointer, point to a block, write data on a block. That's done. Your file is written and it's working as usual. If you need something way bigger than that, you are going to use the yellow indirect block pointers. And what that is that you're going to point to a block that's full of indirect block pointers. So you can fit 246 direct block pointers inside it to be able to get more data. Now you can kind of guess where we're going with this, where the doubly indirect block pointers stores big blocks full of indirect block pointers that themselves store blocks of direct block pointers and then stores data. And the triply indirect block pointers, well, that's a big thing. So this is how we're actually storing that much data inside of the file system, is we're just chaining things around until we have enough pointers to, well, store our data. So this is it for the file part of things. Now let's just go to the directory part of things, because that's where it all comes around. That's where we start making sense of things, because right now we have the ability to create a file, we have the ability to tell where the data is, but how does this file get a name and how does everything else work around this? So this is where the directory table comes in. So of course the directory table is a big table full of directory entries that contains first the inode to be able to point. There's the inode that can point to the data or the other directory. So that's how you do it. Then you have the record length. You have the name length that gives you the length of the actual name that comes after it. And then a name between 0 and 255 characters, which is normally in ISO Latin 1. Now, let's just make an example to make it clear to us how it's really on the drive, right? So if we do an ls command, we're gonna have those information come back from us. We have the dot, which is the directory that we're in right now. We have the 2 dots, which is the directory before us. We have the .bash profile, which is a file. We have .bashrc, another file. mbox, which could be a directory. We have public HTML, probably a directory, and tmp, probably a directory once again. So how does it look on the actual data on the drive? So let's start with the first one, the dot, where we see that we have the inode for the directory that we're in right now. We have the record length, we have the name length, we have the name, which is dot, and we have padding. Now, padding is there to try to make everything 32-bit, because remember, back in the day, your CPU was probably a 32-bit thing, or at least it could realistically eat 32-bit at a time, so it just makes sense to try to fit everything within that size to be as fast to be processed as possible. Now, our second entry, we have the inode for the directory table before us, we have the record length, we have the name length, and the name, which is 2 dots, and again, the padding. And then we have the actual inode for a file, the record length, and again, the name length, the name itself, .bash profile, and again, the padding. So it's just that repeats itself again, and again. So that's how you're actually navigating the file system. You're just going through the first directory, the slash directory, and then you can go down and see all of your data. But if you were inside a directory already, you could navigate from there. So you could go back and you could go up the tree to see what was before you and to see what's down. So it makes navigation as simple as possible to have all of that information about the directory. So now you can understand how EXT2 works, right? Because if we want to write a file, well, we create an inode, we add it to the directory that we're in, and if it's a directory in and of itself, well, we will create the directory table to go with it, and now we're able to put data into that directory table. And for the blocks that are allocated, we just need to add our pointers to the inode to be able to know where the data was set. We need to check the blocks that we used in the block bitmap, and we're done. So it's really a simple thing. Well, when you put it like that, it's really simple, but it was a complicated beast, right? Because you needed to make all that and make it optimal as possible. But EXT2 was a really smart project, and just the fact that they use blocks the size of the memory pages was already a big performance boost. And you see everywhere that they, well, implemented things, it was all with performance in mind. Everywhere that you see padding, of course, yet again, performance in mind. So this is it for EXT2. Now you know how it works, now you know where it comes from. All that's left for you to know is how does EXT3 works? Because that's what's fun with EXT, is that soon enough I'll be able to make a video about EXT3 and actually explain to you how EXT3 works, and it will just make sense because it's really just EXT2++. When making this EXT2 video, it was really hard to try to divide what was part of just EXT2 but was upgraded until it was EXT3 and what was EXT2 the day of its creation. So that's what's really fascinating, is that idea of leaving some space for upgrades made this file system so superior to whatever happened in the past. That's why we don't know what XiaFS even is, but we all know what EXT is. So that's all for this video. I hope you enjoyed. You probably saw that I put a little bit more effect. I'm trying to learn a little bit how to make DaVinci Resolve work. So yeah, I'm messing around, but I hope you still enjoyed with the flashy new things that I'm adding. And of course, take care.